Hello, AP Chem. I have a new um, presentation. This is 6.A.2. Remember, we are in Unit 6 or Module or Big Idea 6, Equilibrium. Any bond or intermolecular attraction that can be formed can be broken. These two processes are in dynamic competition, forward rate, reverse rate, and they're going to be sensitive to initial conditions. So we're going to talk about these initial conditions today. Later, we will be talking about external perturbations. So just to review, you start out a chemical reaction that's going to reach equilibrium. You have a certain amount of reactant. The forward reaction slows down as you use up your reactant. The reverse reaction speeds up as you form more product. At some point, they become equal. That is, the forward rate is equal to the reverse rate. The reactant concentration is not equal to the product concentration. It's just the forward rate equals a reverse rate. One rate is favored over the other, and so you're going to have more or less of either reactant or product. But you reach an equilibrium state where the two rates are equal. Now, once you reach the equilibrium state, because you are forming and using up reactant and product at the same rate, your concentrations don't change. Because your concentrations don't change, your rates don't change, and as a result, you have reached a stable situation where nothing is changing except it is dynamic. You do have the forward and reverse rate still occurring. They're just not resulting in any change. That's what we call equilibrium. Now, it's important to understand that when we are looking at one of these equilibrium situations, we would like to know whether or not we are at equilibrium or not. As you recall, at equilibrium, the product over reactants equals some constant, the equilibrium constant, capital K. So it's often useful to evaluate whether or not your products over reactants are equal to K, greater than K, or less than K. So that's what we do, is we determine the current state of the system undergoing the reversible reaction. And we characterize it by looking at the extent to which the reactants have been converted to products. So that means we look at the relative quantities of the reaction components, the products and the reactants, and we quantitatively or mathematically calculate something called the reaction quotient Q. So in general, we've been saying that what we're looking for is the ratio of products over reactants in order to determine whether or not they equal the equilibrium constant or not. But more specifically, what you want is the molarity of the products. That's what the square brackets in this blue box represent. The square brackets around C and D and A and B are molarity, moles per liter, which can be used for aqueous or gases. You can take the moles of a gas per liter or the moles of aqueous solute per liter. But we also need to raise them to the power of their coefficients. So what we do, let's say we have a generic reaction that A plus B makes C plus D, and it's going to result eventually in some equilibrium situation, and we want to evaluate whether or not we're at equilibrium yet or not, and if so, if we're not at equilibrium, what direction do we need to move to get to equilibrium? What we would want to evaluate for our reaction quotient Q is the molarity of chemical C raised to the power of little c, the coefficient of that reactant, of that product, times the molarity of D raised to the coefficient of D, divided by the quantity molarity of A raised to the power of its coefficient little a, times the molarity of B raised to the power of its coefficient little b. So that is more specific than just saying products over reactants. It's very specific as to how you take and calculate the value of the product in the quotient and the reactant in the quotient. Remember, it's just everything's molarity raised to their power. So let's look at the law of mass action. Now the law of mass action applies to a situation where you are at equilibrium. At equilibrium, here we have our generic reaction AA plus BB makes CC plus DD. At equilibrium, your forward rate equals your reverse rate. So if we look at our forward rate as an elementary step and our reverse rate as an elementary step, then if we think back to our kinetics, the forward rate would be Kf times A raised to the power of little a times B raised to the power of little b. And that's equal to K reverse, because a reverse reaction is equals a forward reaction. K reverse, molarity of C raised to little c, molarity of D raised to little d. Now, if we rearrange this, we get K forward over K reverse equals C to the C, D to the D over A to the A, B to the B, which, as you recall, is the reaction quotient. Now, the reaction quotient, if you are at equilibrium, which we've been describing this situation to be at equilibrium, is not only equal to Q, it's also equal to K, capital K, the equilibrium constant. Now, in this particular case, since we're using concentration, we've designated our K, K subscript C, little c subscript for concentration. We could, if it were, say, a gaseous equilibrium, we could possibly be looking at these, we wouldn't have to, but we could look at the amounts of C, D, A, and B in terms of the partial pressures of those gases. So the partial pressure of C raised to the little c power, the partial pressure of D raised to the little d power, divided by PA to the A, PB to the B. If we were using pressures in atmospheres, we would say Kp is P for pressure. So capital K, little vocabulary, capital K is called the equilibrium constant. And its numerical value is that ratio of C to the C, D to the D over A to the A, B to the B when the quantities of the reactants and products are at equilibrium. If you're not at equilibrium, that ratio is simply Q. But when you're at equilibrium, it is also K. The equation for K is called the equilibrium expression. So many times on the AP test, they will ask you to write the equilibrium expression. So don't just write the right side, write the entire equation. The equation for K is called the equilibrium expression. K equals C to the C, D to the D over A to the A, B to the B. We calculate K, of course, the same way we calculate the reaction quotient Q, except for the reaction quotient, you don't necessarily have to have equilibrium quantities. The reaction quotient is used to evaluate whether or not you're at equilibrium. If you are at equilibrium, then you plug in the numbers for the equilibrium concentrations or pressures, and you get the equilibrium constant. Now, this is a little different than kinetics. In kinetics, we cared a lot, and we were very specific on what the units were for little k. For capital K, we don't care what the units are. We generally express it as a unitless number. So in your answers for big K, you'd never put units. Just a little bit of difference between how we do kinetics and how we do equilibrium. Now, let's talk about these ICE tables. This is how we do the algebra on a problem where we are given some initial conditions and asked to evaluate the equilibrium conditions. So given an initial set of reactant and product concentrations, only those sets of concentrations that are consistent with reaction stoichiometry can be attained. For instance, it doesn't matter how much A and B and C and D you start with. When you shift to reach equilibrium, you have to shift based on the stoichiometry of the reaction. You can't shift the amount of A, B, C, and D without reacting all of the reactant and forming all of the product. You can't just move A over and call it C. You've got to move A and B over and call it C and D, for instance. So these tables are very useful for determining the concentrations that are possible at equilibrium. So a typical ICE table, some people call them RICE tables, they'll label the reaction R and then the next three lines ICE. RICE is used for these ICE tables because what we're doing is we're doing initial, change, and equilibrium. So initial is the molarity of A initially, molarity of B initially, molarity of C initially, and molarity of D initially. Now we're going to change in either the forward or the reverse direction in order to reach an equilibrium. So we say plus or minus little a x. X is the amount of shift the reaction needs to undergo, and that will be multiplied by little a. If I run the reaction once to the right and the coefficient of A is 2, that means 2 A's get used up. So that's why we have the multiplier of the coefficient. So plus or minus AX, plus or minus BX. If I could make the fonts do it, I'd say minus or plus CX, minus or plus DX. So then we evaluate at equilibrium, the amount of A we'll have at equilibrium will be A, and then plus the change, plus or minus AX, B plus or minus BX, and so forth. Now just to illustrate how that works, here we have an equilibrium where we have N2 plus 3H2 makes 2 NH3s. Now we're adding initially to this container 4.50 moles per liter of N2 and H2. Notice the unit moles per liter concentration. No ammonia is initially present, so we don't have any ammonia in the container at the beginning. So at equilibrium, it says that the concentration of NH3, because we have reached equilibrium, is now 1.50 moles per liter. So then let's find all the concentrations of N2 and H2 if we assume no temperature or volume change, no external perturbations. So to work this problem, I would set up an ICE table like this. I would say initially the N2 is 4.50 molar, the H2 is 4.50 molar, the NH3 is 0 molar. Our change, and here we're going to know what the plus or minus is because we know we need to shift to the right. We have no NH3, we can't do the reverse reaction, we have to go forward. So we know we're going to subtract from the left and add to the right. So we're minus x for our change for N2 because the coefficient of N2 is 1, minus 3x for the H2 because the coefficient of H2 is 3, and plus 2x for the ammonia. So putting the initial and change together, we get the equilibrium number for N2 to be 4.50 minus x, 4.50 minus 3x for H2, and 2x for NH3. Now this one's fairly easy because they told us the concentration of NH3 at equilibrium is 1.50 molar. So using 2x equal 1.50 molar, I can get the x value to be 0.750 molar. Plugging that back into the equilibrium formulas for N2 and H2, I get 4.50 minus 0.75 is 3.75. 4.50 minus 3x is 2.25. So this reaction quotient Q is going to provide us a convenient measure of the current progress of a reaction. Q does not include substances whose concentrations are independent of the amount of substance. For example, if the moles per liter of a chemical is not going to change, then you don't need that concentration included in the equation for Q. You can just use it as part of the constant. So a solid, for instance, aluminum is a density of 2.7 grams per cubic centimeter and a molar mass of 27. So that means a liter of aluminum is going to weigh 2.7 times 1,000, so 2,700 grams. 2,700 divided by 27 is 100 moles per liter. The molarity of solid aluminum is 100 moles per liter. There would be no need to include that in the Q expression because 100 moles per liter is going to be constant for the solid aluminum at all times. So we don't need to include a solid as part of our Q or our K expressions. Also liquids, pure liquids. Now aqueous we do, but a pure liquid like water, water has a molarity of 55.5 moles per liter regardless of the state of the equilibrium. the liter of water always is 55.5 moles. So we have these liquids and solids that may be reacting and may be in contact with a gas or maybe in contact with an aqueous ion, but we don't include them in the Q expression. So pure solids, pure liquids, don't include them. Q only includes gases and aqueous substances. Now just a reminder, if our Q is less than our K, it means our products over reactants ratio is too small to be at equilibrium. So if our products over reactants ratio is too small, we need to make more product and use up some of our reactant to get the ratio in line with the equilibrium values. So that means if our Q is less than our K, we need to shift to the right, to the product side. We need to move some of our reactant over to the product. And likewise, if Q is greater than K, we need to shift to the left. We've got too much product. We need to shift to the left. If Q equals K, we're at equilibrium. Okay, let's do another problem. This one will not require an ice table, but I am going to use the I in the ice table just to label what the initial molarities are. The reaction below is being studied. The equilibrium constant has a value of K equal 0.045 at 25 Celsius, so we're given the K value. If the molarity of the water vapor, now this isn't water liquid, this is water gas, so this is included in the Q expression. If H2O is 0.34 moles per liter, H2 is 2.3 molar, and CO is 2.3 molar, which direction are we going to shift to get back to equilibrium? So initially we have 2.3 molar H2, 2.3 molar CO, and 0.34 molar H2O. Notice I have ignored the concentration of carbon solid because carbon solid is a solid and its molarity doesn't change, and so we do not include it in the Q expression. So to evaluate my Q, I take my product, water, over my reactants, which are H2 and CO, so 2.3 times 2.3, or 2.3 squared, and I get 0.0643. 0.0643 is greater than 0.045. So it's telling me the top of my ratio is too big and the bottom of my ratio is too small. So to correct and get back to equilibrium, I will need to use up some chemical on the right side and make the top smaller and move it over to the left side and make more reactant. Too much product. So we would say we need to shift left. We need to move the reaction in the leftward direction until we reach equilibrium. The value of Q, and as a result K, is going to be evaluated differently if you reverse the reaction. If you reverse the way the reaction is written, if you say, no, that's not the product, that's a reactant, and no, that's not the reactant, that's the product. If you flip the reaction, as you saw in thermodynamics, sometimes we flip a reaction, what you have to do then is realize you have taken the reciprocal. You have moved the product and reactant and reassign them, and so you have to flip the top and bottom of your equation for Q or your equation for K. Also, if you're adding together reactions, let's say just like in Hess's law, we want to add a reaction to another reaction, you would need to multiply the K values for that. Likewise, if you multiply a reaction by a constant, say you double a reaction, you will need to square the Q or the K value for that particular reaction. So to answer the question in red down at the bottom, how is the value of Q or K affected by writing the reaction in reverse? It means that the Q or K is flipped. It is reciprocal. So let's take a look at an example of that. We have 2NO2 gas yield N2O4 gas. That's an equilibrium. And the K value for that is 0.56. What would be the K value for the reaction N2O4 yields 2NO2? Actually, I have made a mistake here. I thought we had divided the reaction by 2. We did not. So I said K equals 1 over 0.56 square root. Actually, it's just K equals 1 over 1.56. So Okay. So actually, my answer should be 1.79 or 1.8 on this question. Sorry about the mistake there on the, there's a little mistake also up in the way the question is read. I forgot to put k equals 0.56. So the k equals 0.56 for the reaction. If you flip the reaction, k equals 1 over 0.56, and so that's 1.79. Okay, here's another example. We have ammonia plus water makes NH4 plus OH minus. K equals 1.8 times 10 to the minus fifth. We also have H plus OH minus makes water. K equals 1 times 10 to the 14th. What would happen if we add those two reactions together? If we add them together, the waters will cancel and we'll get H plus NH3 makes NH4 plus. Also the OH minuses would cancel. So adding two reactions together means that you need to multiply the K's. So multiplying the K's would mean we get 1.8 times 10 to the minus fifth times 1 times 10 to the 14th, which comes out to 1.8 times 10 to the ninth. So even though the ionization of ammonia and water to make hydroxide has a very small K, if you react the OH minus with H plus, then in other words, you add acid to your NH3, then an acid plus NH3 actually has a K that's very large. NH3 reacts very slightly with water, but it reacts completely with acid, H plus. Okay, so here's some homework to try. 1414, 1420, 1424, 1426, 1428, 1430, and 1432. So it's some practice with just the concept of how to calculate some Q's and some K values based on this, the principles of the algebra of Q and K. Thank you very much.